Imagine you are holding a rope in your hands. You twist it, loop it, and tie it into a knot. No matter how hard you pull on the ends, the knot doesn't vanish. It remains a locked configuration, a structure held together not by material, but by geometry itself. Now imagine that instead of a rope you were playing with the invisible threads of the quantum world, the swirling fields that underlie matter and energy. What if those fields themselves could tie knots? And what if those knots weren't just abstract mathematics, but real, physical structures that could exist in the strange fabric of the universe? This is the world of quantum knots, and in this world live two of the most fascinating and mysterious creatures physics has revealed, Hopfions and Skyrmions. For most of human history, knots were just tools. Sailors tied them to control ships, climbers used them to survive on cliffs, and we use them every day without thinking. But in the late 1800s, physicists briefly entertained a radical idea. What if atoms themselves were knots in the ether, an invisible medium once thought to fill space? That idea faded when quantum mechanics and atomic theory rose, but in a strange twist of history, the concept of knotted matter has returned. Not in the ether, but in the powerful dynamic fields that define modern physics. Fields are the stage on which the drama of the universe plays out. The electromagnetic field gives us electricity, magnetism, and light. Quantum fields create the particles themselves, but fields are not static. They can twist, curl, and sometimes tie themselves into stable knots. And these knots, bizarrely enough, can act like particles. They carry energy, they have momentum, and they resist destruction because of a deeper law of mathematics called topology. The simplest way to picture this is with smoke rings. Blow a perfect smoke ring and you see a stable loop of swirling vortices. It doesn't immediately dissipate because its structure protects it. Now imagine a smoke ring not of smoke, but of fields, self-sustaining, stable, and woven into the very language of quantum reality. That's what physicists call a Hopfion or a Skyrmion. Skyrmions are perhaps the most accessible. First described by the physicist Tony Skyrm in the 1960s as an attempt to describe protons and neutrons, they turned out to be far more universal. In many modern materials, especially magnetic crystals, Skyrmions appear as tiny whirlpools of atomic spins. Imagine a flat sheet of atoms, each with a little arrow pointing in the direction of its magnetic orientation. Normally, all those arrows line up neatly, but under the right conditions, those spins twist into a spiral. At the center, the arrow points down. On the outer edges, it points up. In between, it smoothly rotates. What you get is a particle-like swirl embedded in the magnetic field itself. That swirl is a Skyrmion. These structures are unimaginably small. Billions of them could sit on the tip of a pin. Yet they're incredibly stable. You can move them with electric currents, you can push them around, but you can't easily destroy them because they are protected by topology. They are like whirlpools in a river that don't fade away, or knots that don't untie themselves. And here's why scientists are excited. Because Skyrmions are stable, tiny, and controllable, they could revolutionize computing. Each Skyrmion could represent a bit of data, allowing for storage thousands of times denser than today's hard drives. Imagine processors that barely consume energy, or artificial brains where information flows like patterns of these whirling quantum knots. Labs are already experimenting with Skyrmion-based devices, and some researchers believe Skyrmions may become the building blocks of a whole new generation of technology. Hopfions, however, are even stranger. Where Skyrmions are two-dimensional vortices that extend through space, Hopfions are true knots, higher-dimensional tangles of field lines. To picture this, imagine wrapping a rubber band around a donut. You can loop it once or multiple times, and you can twist it before closing it. The way it wraps determines its knot. Hopfions are like this, but instead of rubber bands, they're loops of field lines in space, linked and knotted together. In a Hopfion, every loop of field is linked with others. forming a complex braided structure that sustains itself. For a long time, Hopfions were thought to exist only in abstract mathematics, described in the elegant geometry of maps between spheres. But in recent years, researchers have found evidence that Hopfions can be created in exotic materials, in plasmas, even in light itself. They may also exist naturally inside nuclear matter, or in the strange conditions of the early universe. What makes both Skyrmions and Hopfions special is topology. Topology is the branch of math that doesn't care about distances or angles, but about fundamental structures. In topology, a coffee cup and a donut are the same thing, because each has one hole. A pretzel with 3 holes is different. The number of holes is a topological invariant. For Skyrmions and Hopfions, the invariant is the way fields twist and wrap. You can stretch the field, you can distort it, but as long as the knot remains intact, its topological number doesn't change. That's why these knots are stable. They are protected not by energy but by geometry itself. To untie them, you'd have to break the fabric of the field. To make sense of this in daily life, think of shoelaces. When you tie a knot, it doesn't undo itself no matter how you shake your foot. To undo it, you have to carefully work against the structure of the knot. Skyrmions and Hopfions are like shoelace knots in invisible strings made of quantum fields. Or think of DNA. DNA strands naturally form loops and knots, and enzymes have to cut and rejoin them to untangle them. In the same way, Skyrmions and Hopfions require precise surgery to destroy. Left alone, they persist. They are patterns that defy decay, and this is where the implications get cosmic. Some scientists suspect that in the earliest moments after the Big Bang, the universe was filled with field configurations like these. As the universe cooled, some knots may have survived, frozen into the fabric of reality as cosmic relics. Perhaps some of the strange phenomena we call dark matter are actually topological knots in fields, hiding in plain sight. There's even a bold idea that particles themselves, protons, electrons, even quarks, might one day be understood not as fundamental points but as knots in the quantum vacuum, stabilized by the geometry of fields. If this is true, then reality itself is not built from blocks but from braids and knots, a grand tapestry woven out of invisible threads. The potential applications are staggering. In computing, Skyrmions may power ultra-dense, ultra-fast, energy-efficient memory devices. In quantum technology, Hopfions may hold the key to fault-tolerant computation, where information is stored in topological knots immune to noise and error. In energy research, plasma knots could give us new ways to stabilize fusion reactions, helping us tap into the power of the stars. Far from being just curiosities of mathematics, these knots could reshape the future of civilization. And yet, even beyond applications, they invite us to think differently about reality itself. When you tie your shoelaces or untangle your headphones, remember that the universe may be doing something similar at a level you cannot see. Invisible knots may be tying together the threads of matter, shaping the stability of the world you live in. Skyrmions and Hopfions are whispers from nature, showing us that stability and identity don't always come from particles, but from patterns, from geometry woven into existence. Perhaps, when we finally master these quantum knots, we'll realize that the universe itself is a grand knot, infinite and eternal, a braid of fields and energy and geometry waiting to be untangled by curious minds. Until then, every time we see a knot in the ordinary world, we should wonder, are we glimpsing a reflection of the deepest structures of reality?